In this video we're going to discuss frequency and period of simple harmonic motion, and then we're going to do some pretty fun derivations of how we get these formulas for our period and frequency. So for springs, the period and frequency are given by these equations, where it's only dependent on the mass and the spring constant. So to visualize what this looks like, if we had a spring that was like this, and we released it from rest, and it traveled this way until it reached its max point, and then traveled back to reach its minimum point here, and let's say this was equilibrium, the period t would be given by this equation. And we know that frequency is just 1 over the period. So if we wanted to find the frequency, we would just 1 over t, and so if we plugged in this equation, we would get this for frequency. Okay, so let's do a quick example on using this formula. So we have a block of mass m is attached to a spring and set into simple harmonic motion. If the block was replaced with a block of 4m, how would the frequencies compare? Okay, so we know the frequency equals 1 over 2 pi square root of k over m, and so we define it as big M. So if we say frequency 1 is this equation, and if we want to find the second frequency, we can go ahead and plug in the mass of this, which is 4m, and this should be big M. And so now we can try to get this equation inside of there. And so if we pull out 1 over the square root of 4, and then in here we just have 1 over 2 pi square root of k over m, well, this piece right here, and this should be equals, this piece right here is just f1. So now we can rewrite it as f2 equals 1 over the square root of 4 is just 2, so we have 1/2 f1, and that would be our relationship that we can derive using that equation. Okay, and so a similar formula is for pendulum motion. In this case we have L, which is the length of the pendulum, over gravity, which is just the constant. And so this formula is used to describe the period and frequency of a pendulum that swings down this way and then comes back, and that would be the period. Okay, and so this equation can be used just like the other one if we wanted to compare given different lengths. And so notice that the angle that the pendulum starts at does not change the period of the frequency of the pendulum. And same in the last example, how much the spring was compressed also didn't change how fast it goes back and forth, which is interesting, because if we had a pendulum that started at this point and then maybe one that starts, let's do it in a different color, one that starts, say, at this point, it would take the same amount of time to go here to here than the one on the outside to go down and back. And that's because it's going to be moving faster, because that's to cover more distance. And that's the same exact case as if we had two springs. Let's say one was stretched out like all the way out here, and one was just to here, and let's say this is the equilibrium. The time it takes for this one to go all the way here and then all the way back would be the same time it takes this one to go here and back. And that's only going to be for simple harmonic motion cases, which is kind of an approximation. And so for this pendulum, this equation, or these both equations, will only hold true when the angle is less than or equal to 15 degrees starting. And we'll see why that is, because I'm now going to derive both the equations for the springs and the pendulum. And so this derivation is quite long, and it's really not something that you'd be asked to do in a class most likely. And if this is for AP Physics 1, they give you these equations on the formula sheet, but I think knowing where these come from, one, is just really interesting, but also kind of gives you more of an understanding of why we can just use these approximations and what approximations we're actually making, and why is it that 15 degrees can only be used. Okay, so let's do these derivations. So let's start by trying to derive an equation for the period of a spring going back and forth. So remember, what we're trying to find here is if we had a spring, let's just say on a level ground to make this easier, and it stretched out some distance, which we'll find out doesn't matter, the distance, how long would it take to go down and back, right? So that's what we're trying to figure out. So the way we're going to do this is quite interesting. So let's imagine we have a table. And we'll see how well we can draw a box here. So let's say we had a table, and we're looking at it from the top down. And on this table, there's an object moving in circular motion. So let's say there's an object and it's moving around in a circle. Okay? So this object's moving in a uniform circular motion, so the velocity at every point, we'll say, is equal. So it's uniform circular motion, velocity is equal everywhere, and it moves around in this circle. Okay? Now let's say you view this table from the side. So that's an eyeball right there. So now we're going to have a little table here, and we'll try to draw this out. What you're going to see is this motion in only one direction that comes down, reaches an endpoint, and then comes back. And I'm trying to kind of draw a motion map here to show how the velocities change. But you can see when it gets to the end, it's going a lot slower in distance, or slower in velocity when you're viewing it from here. But you can see on the outside, the velocity is going to be constant. But what we're actually viewing from the side is just the x velocities up here. The velocities in the horizontal direction rather than this vertical direction is what we're viewing down here. And so a few things we can notice here is that, one, the radius of this circle is going to be equal to the change in x if we are viewing this as an oscillator. So this would be kind of the same as seeing a spring going back and forth, right? Okay, and so this change in x equals to the radius of the circle from up there. We'll also notice that the velocity will be a max at the center here. So we have v max. Okay, and so this v max is actually just going to be equal to the v here, because this v is not changing. What we're seeing is these v's right here are the v maxes. That's just because this v is all vx in this case. So this vx just equals v at these two cases right here. Okay, so v max really just equals v from the circle. Okay, so now we can use these. So we want to find, we need an equation with the period. So we've learned in circular motion that the velocity when going around in a circle just equals 2 pi r over the period. And that's because this is the circumference over the time, right? So that's like distance over time gives you velocity. And so what we're going to do is, instead of calling this change in x, because the change in x could be different at each point, right? We're going to call this the amplitude. So we'll call this big A, which is like the max change in x, basically. So it's the farthest that it comes out. And so since this radius equals the A when you're viewing it from the side here, we can say that this is 2 pi times A over the period. And this is the period we're trying to derive right here. Which equals, since this V is just V max, equals V max. Okay? And so now we have this expression. Alright, so let's go ahead and rewrite this for the period. So we can just simply say that the period is equal to 2 pi A over this V max. And so we can also write this as 2 pi times A over V max. And so we're trying to derive this equation for t. We knew that it had 2 pi times the square root of the m over the k. So that's what we want to get an expression for a over v max for. Because, if you're measuring something, it's nice if you only need to know the spring constant and the mass to determine the period. But in this case, we have amplitude and the max velocity. So we're going to have to find an equation for amplitude over max velocity. And to do this, we're going to have to actually use the energy of the spring situation here. And so we actually haven't learned about spring potential energy yet, and we'll learn that in a little later video where we talk about energies of simple harmonic oscillators. So a little preview into that is that the potential energy of a spring is 1/2 k change in x squared. Okay, and then the kinetic energy is just going to be the kinetic energy as any translational motion of 1/2 mv squared. Okay, so since we're using the simple harmonic oscillation approximation, we can use conservation of energy. So just like normal conservation of energy, we'll have kinetic energy initial plus the potential energy initial, in this case spring potential energy, equals the kinetic energy final plus the potential energy final of a spring. And so what we're going to look at are two initial and final points. Is initially, we are going to say the spring is at this center point right here. We're going to say this is the initial position x naught, which equals 0. And the final is going to be at the amplitude. So that's going to be our change in energy that we're looking at from the initial point to the final point. And they should be equal. But at the initial point, there's going to be no potential energy because there's no change in x, right? They're directly proportional, or not directly proportional, but they are proportional. So when change x is 0, the potential energy is 0, so that goes to 0. Okay? And then at the max point, we learned in the previous video that when the spring is at the max, the velocity equals 0 because it's changing direction. And you can see in the circular motion example, at this max point, there's no x direction velocity, and so that's why our velocity is 0 in that case. So our kinetic energy final is going to be equal to 0 as well. Okay, so we just have kinetic energy initial equals the potential energy final. And so we just learned the equations for those. mv squared equals 1/2 k change in x squared. But now, when we have this initial kinetic energy right here, it's at this point right here. And what is the velocity at that point? Well, it's the max velocity. That's how we define the max velocity. And so first off, we can just go ahead and get rid of these 1/2s. They cancel. And so we'll just have mv max squared equals k. What is the change in x at the max point? We define it as the amplitude. So we have a squared. And now you can probably see where we're getting at here. We can divide the velocity and the k to get m over k equals a squared over v max squared. And when we take the square roots of these, we get that a over v max equals the square root of m over k. And so we can go all the way back to our equation that we were deriving before, where the period equals 2 pi a over v max, and we can just substitute this in right here, and we get our period of a spring is 2 pi the square root of m over k. And so that right there is the equation that we used before. So yeah, pretty cool derivation for the spring. Kind of using a circular motion to show simple harmonic motion and comparing all the variables, using stuff from circular motion, stuff from energy. It's pretty cool. And now we can derive the pendulum equation from this equation. So we're actually going to need to do this derivation to do the pendulum one, at least in the way that I'm going to do it here. There may be other ways of doing it. But since this one uses more of an approximation of angle, we'll have to see where that comes in. So let's go ahead and do that now. Okay, so let's just recall what we're even going to try to derive here. So let's draw out our pendulum, and start doing stuff with it. So we have our pendulum. I'm going to bring this down here. So we have a pendulum that comes out, and it has an equilibrium point. This is at the center of the pendulum, and it has two ends, right? And it's going back and forth in this simple harmonic motion, right? So we have some degree that it can be pulled out to, and so let's try to figure out some things that we can use to derive this equation, right? So first of all, let's look at what does the motion look like. So this pendulum is going back and forth along like a curve, right? It's not going in a straight line, right? It's going along a curve. And so the distance that it's traveling, we'll call from here to here, we'll call x. And so we learned in circular motion, or rotational motion actually, that the angle is equal to this s over r, where s is the arc length. Well, this x right here is just this arc length. So we can say this equals x over r. Okay? And so we get an equation, x is equal to r times theta. But what is the r? Well, the r is the radius from where this arc is being made, which in this case is the length of the pendulum. Because that is, if we made a big circle with this right here, we would get a radius of L. So this x really equals L times theta. So now we have it in terms of variables that we can work with. Okay? And so to get simple harmonic motion, we need the resistive, or the restoring force, to be proportional to x, which in this case it would need to be proportional to theta, okay, to get simple harmonic motion. So that's what we need. Otherwise we won't have simple harmonic motion. And so let's figure out what this restoring force equals. So we're going to have to do a free body diagram on this pendulum. So we're going to take this max point here and draw our forces. So we will have a tension force in the pendulum, Ft, and then we'll have our gravitational force. And we'll have our gravitational force right here. Okay? And so those are the only forces we actually have. So I'm going to draw this off to the side here because it's going to get kind of messy. So let's just draw our basic free body diagram first, right, with just the tension force and the gravitational force. Okay? So this restoring force is what's pulling this pendulum back down, which is going to be the force right here. And we'll call this Fr. And actually I'm going to do this in a different color because it's not a new force. It's just a component of one of these forces. And we can see that what it actually is just the x direction of gravity. Okay? So our restoring force, Fr, will say it equals Fg in the x direction. And so what does Fg in the x direction equal? We see that our gravitational force in the x direction is just going to be the mass times gravity times, it's going to be sine of this theta. And the reason is because this theta is coming off of the vertical axis. So usually x is cosine, but since it's coming off the vertical, this Fgx is opposite of this theta, so it'll be sine of theta. Okay? And so we see that our resistive force here is proportional to sine of theta. So we don't have, that means we won't have simple harmonic motion. Right? So what we need is this to be proportional to just theta. But it turns out that this is our approximation here, that when theta is less than or equal to 15 degrees, sine of theta is about equal to theta in radians. Okay, so that's going to be our approximation right here. And you can test it out if you have to use radians, or at least convert your degrees to radians, because the angle is not going to be in degrees, right? It's going to be in an angle. But you will get a radian that is about equal to the sine of theta. Okay, so now, using this case where theta is less than or equal to 15 degrees, we can say that this restoring force is proportional to theta, because the restoring force is proportional to mg sine of theta, but we said they're about equal, so we're going to say theta only when theta is less than or equal to 15 degrees. Okay, and we could find the radians for that as well. Okay, so let's use this approximation going forward and see what we get. So now we have the restoring force is equal to mg theta. Okay, and now we derived before that theta is equal to x over L, and so we did that up here where x over r, but we said r was equal to L, so theta is equal to x over L. And so we can use that and plug that in for theta. So now we have the resistive force is equal to mg x over L. Okay? And so now what we can do here is we can actually get this in terms of what spring force looks like. And you can notice that mg over L times x, we had the same thing when we had the spring force equals to kx. And this is magnitude. We could have a negative in both these situations as well, if we took the direction of gravity and whatnot. So we have this where, in this case, where k is equal to this mg over L. And so what we can do is actually take our equation for a spring where we have 2 pi over m over k. And we can actually plug in this for our k to get our pendulum period. And so to get a period of a pendulum, we can plug in what we got for k, and so we'll have mass over mass gravity over L. And so we can go ahead and plug these in and get the period is equal to 2 pi square root. And so this will be, the masses will cancel here. And then it will be 1 over g over L, so those will flip around, and we'll get L over g when theta is less than or equal to 15 degrees. So there we go. That's our derivation for the period of a pendulum. So that was also a very long derivation that used the previously very long derivation. But I think it's good to do just to see where everything is coming from and why we had to make that approximation. Because we can't use simple harmonic motion if it's proportional to sine of theta. It has to be proportional to the distance or the angle. Okay? So we can go back through and see everything we did there. A nice long derivation, pretty cool. So leave your questions down below about anything. Again, you probably won't be asked to do this in a class, I would guess. Definitely not if you're in AP Physics 1. But understanding where it comes from could be asked. So you might be asked, like, why is the approximation 15 degrees? Well, you have to say because it needs to be proportional to the angle and not sine of theta. So something like that might be asked, I guess. So yeah, thank you all for watching, and I'll see you in the next one.